Welcome to the T-Navigator Knowledge Series. This series is designed to provide an in-depth look at how the T-Navigator software is transforming the way the energy sector approaches complex simulations. Each episode that we'll go through in this T-Navigator Knowledge Series dives into a specific feature of the platform, showing you how to maximize its potential. Whether you're optimizing oil production, driving clean energy innovation, or advancing carbon capture and storage projects, you'll find the tools and insights you need right here. In this week's episode, we have Naquib Amin from a Kuala Lumpur office discussing managing uncertainties in CCS projects.
In carbon capture storage study, in which you are injecting and storing a large quantity of carbon dioxide into a subsurface formation, numerical simulators become an essential tool in the preparation stage, in which we call pre-processing and modeling, during the injection operations and after injection period, in which we see how this injected fluid will react and stored within the formation for a period of time. When you are looking at this study that spans a long period of time, of course, there will be questions of how much carbon dioxide can we store, how is the carbon dioxide being stored, and which mechanism works best for storage, and also if there is any possible migration or leakage. Now, these are uncertainties in which we have to define the known knowns, the known unknowns, and the unknown unknowns. So, how does the navigator comes to play in this particular case study? T-Navigator offers an integrated solution in which it is capable to include parameters across different domains and perform calculations implicitly using one pressure system. Now, through this integration, uncertainties can be catered within three steps. Step one, workflow setup to capture all uncertain parameters in a workflow which integrate the designer modules across geology designer, model designer, network designer, along with PVT and well designer. Step 2, design of experiments, in which multiple variants and cases will be created based on selected algorithms. Algorithms such as Monte Carlo, Latin Hypercube, Tornado, Plackett-Berman are all available in AHM module to randomize according to the values ranges that were defined in the workflow. Last but not least, step 3, conducting analysis based on the randomized variance and uncertain parameters. Now, TNAV allows you to do results analysis across different modules, aligning itself with the idea of TNAV being an integrated solution. Over here as well, you're able to select the most ideal case to be transferred back into the designer module and turning it into a legacy model. An example of a case study is an injection case into the permeable aquifer in Johansen Formation. Now, carbon dioxide was injected for about 100 years and then were subsequently stored for an observation period of 500 years post injection. Again, going through the steps, step one is to set up an uncertainty workflow. In here, we are including geomechanical properties, relative permeability curves such as endpoints, aquifer parameters, data relating to well structure, impurity components, as well as operational constraints. Then, through step two, in terms of generating multiple variants from these uncertain parameters. For the uncertainty analysis, we are able to observe plume distribution and compare how much CO2 is being stored and which trapping profile is affected by varying the uncertain parameters. There is Pareto chart, cross-plot, histogram in AHM module to help us with this sensitivity analysis. A second case study emphasizes on grid scalability and how it affects the capturing of carbon dioxide gas through the different trapping mechanisms. Now in here, grid is refined down until there is minimal difference in the amount of trapped CO2. Over here as well, you can see that T-Navigator is able to handle up to 11 million cells for CCS model coupled with geomechanics feature. Case study 3 focuses on CO2 injection for enhanced gas recovery. Now, this case is using compositional version of Groningen field. Groningen field is a brown gas field with about 40 years of production data. In this particular case study, what we are looking for is to improve enhanced gas recovery or EGR process via huff and puff method. Hence, an optimization workflow via customized Python script was actually designed to identify the optimum injection and shut-in period in order to gain a higher recovery. Last but not least, case study 4 incorporates integrated network model by attaching surface facility with a complete set of wellbore models together with a reservoir model. For this particular case, we are able to include many more uncertainty parameters, especially the surface constraints, such as injection rate, pressure, compressor, and tubing inside diameter into the case study. Now, these four case studies display T-Navigator capabilities in managing uncertainties for CCS modeling. Since we are working in a cross-domain environment, one integrated solution is needed to ensure the effect of uncertainties are being kept in one implicit system. Thank you very much.